We present SNARF, Differentiable Forward Skinning for Animating Non-Rigid Neural Implicit Shapes. Neural implicit representations have emerged as a powerful tool to capture geometry at high fidelity with flexible topology. However, most approaches focus on static scenes only. In this work, we propose to learn a skinning model jointly with the implicit shape, enabling animation of neural implicit avatars. The input to our method is a set of posed 3D meshes in combination with the corresponding object poses. Given this input, we jointly learn a shape and skinning weight representation in canonical space. This allows our model to reconstruct continuous implicit surfaces for unseen poses, even in cases where the target pose is far from the poses observed during training. But how can we deform a continuous function in a differentiable way? Existing methods use backward skinning and learn a weight field conditioned on the deformed point and the object pose. In contrast, in this work, we propose a forward skinning model that learns a weight field conditioned on the corresponding point in canonical space. As illustrated here, backward skinning weights are pose-dependent, do not generalize well to novel poses. In contrast, forward skinning weights do not depend on object pose, and thus generalize more easily to unseen poses. While forward skinning defines the mapping from canonical to deformed space, we also require the inverse mapping for learning a shape model in canonical space. As this inverse relation is a one-to-many mapping, and as it is only implicitly defined, there exists no closed-form solution to it. We tackle this problem by deriving a differentiable forward skinning formulation. More concretely, we first find all canonical correspondences of a deformed point via iterative root finding. We then predict the occupancy of the deformed point by aggregating occupancy information from the set of all roots while conditioning on the object pose. We derive analytical gradients for this process via implicit differentiation to avoid backpropagation through the iterative root finding algorithm. This enables our model to learn both shape and forward skinning weights end-to-end from deformed observations. We now show results on minimally clothed 3D humans. We use 9 out of 10 sequences from the DFAUS dataset for training and evaluate on the remaining one. We first compare the results of our method to the results of NASA on unseen poses from the training distribution. While both methods are able to reconstruct the overall shape well, NASA struggles at joints as it doesn't learn skinning weights. In contrast, our method is able to reconstruct the entire shape well. We now demonstrate results of both methods on poses outside the training distribution. In this setting, the baseline fails completely while the proposed forward skinning model generalizes well. Here is another example with a more extreme pose. We now show results of our method on clothed human subjects. We train our model on the CAPE dataset with meshes obtained from 4D scans. In this setting, we illustrate both the learned skinning weights in canonical space as well as the reconstruction for novel, challenging poses outside the training distribution. While in general, our model captures pose-dependent clothing deformation well, it degrades gracefully for more extreme unseen poses. Finally, as a proof of concept, we also show that our model is able to learn from non-human subjects. To demonstrate this, we chose posed animal meshes from the small dataset for training. As can be observed, our model learns sensible skinning weights and 3D shapes also for animals, which allows for a realistic character control.